Okay, here it is. So here you see the condition of them here. In between each carbon, okay, we can see the sigma bond is happening. So between them here, we're going to have 6 sigma bond, make them the strong bond in them. But in benzene, each of the carbon, they have one last bond going up and down, pi orbitals. Normally, we're going to think of them as going to have couples, so 3 couples. But in this case here, are we going to have left or right for this carbon? There is no way to tell. So what happens actually is they're going to merge all together and become a donut shape. Remember, they always comes in pairs. So there's donut top and the bottom of the plane here. The donut here, top and bottom, is going to press the hexagon in the center so that the benzene will be exactly planar. This is a better diagram, I think. The 6 of them is going to merge together, so there will be some binding in between them. They are not this is a better truer representations than the donut here. They're not going to make them into smooth circle here, but actually this one is better representation. But for simplicity, people usually depict them as if it's a smooth donut here. Actually, it looks much less like a donut. So here it is. This one is also a good representation here. So we have here, there will be a big strong here, a strong area on top and bottom of every carbon, and weaker area in between them. The repulsion from the top and bottom ring makes the benzene perfectly planar. Do understand that all pi bonds are unnecessary bonds. Only the sigma bond is needed in order to join 2 atoms together. So pi bonds are ways of atom to cope with non-bonding electron. So these electrons going up and down here, they are not really needed to join the carbon atoms. They are there just like a reserve electron. Hence, when we put them together here, they are quite reactive. In alkene, they are very reactive and they are ready to react with any electrophile species. But in benzene, because of their full delocalization here, it is harder for us to break them. So in general, it is harder to have any addition reaction in benzene. In fact, it is easier to have exchange of hydrogen than to have any addition, which means the breaking of the donut. I repeat, the stability of the ring-shaped electron bond here means it is easier to exchange the hydrogen into something else in benzene rather than trying to break the bond, make the bond into single. So that is the several key parts of our idea here. So here we have them here. We need to know the general structure, distillate, and skeletal for arene. Halogen, phenol, acid, amino acids, we're going to have them here. Next here, we're going to know about the systematic nomenclature of aromatic molecules, 1 benzene ring, and 1 or more simple substituent. If we have 1 substituent, then the name changes totally. We have had the 7 basic substituents. That's another differences between aromatic and aliphatic carbon. In aliphatic carbon, if this is the major line, anything goes up and down, we call them branch. So we have 3 branches here. But in aromatic hydrocarbon, anything that is not hydrogen in the ring, we're going to call them substituent. I repeat, in aliphatic hydrocarbon, we have the main chain and extra carbon or extra anything to the left and right, we call them branch. Branches plural. But in aromatic hydrocarbon, if we have this benzene as the backbone, anything that is changing the hydrogen, X, for example, or Y or Z, we're going to call them substituent. They are going to substitute the hydrogen, even if it is substituted with aliphatic alkyl. Okay, next we're going to talk about the naming. There are 2 ways of naming it. We need to designate the original substituent, the primary substituent. Let's say we have phenol. Now, the carbon next to phenol, we're going to call them carbon number 1. If there is any substituent on the other position, then we're going to name them such that the second substituent gets the closest number of carbon. Let's say this is having a nitro substituent. Now, we're going to number it clockwise because then this carbon gets number 2 instead of counterclockwise, of which this gets number 6. So this is 1, 2, 3, 4, 5, 6. We're going to number the carbons here, this part. Now, in this case, this is basically phenol. This is the primary branches. We're going to have nitro here in position of carbon number 2. So it's going to be 2 nitrophenol. It may not have any space, yeah? I'm just writing this here so we know how the parts of them. 2 dash nitrophenol without any space. Question here? Now, if we have other substituent, let's say here, another nitro, the name is going to be 2N4. It's going to be dinitrophenol. The first way of naming is using the priority substituent as carbon number 1, and then we put everything here, numbering from that number. Paying attention such that the carbon numbering is going to be minimal for the first branch, no, not branch. So for the first substituent we're going to find out. This is the first way of naming using number. Another way of naming is what happens if we have 2 substituents. The second numbering can only have 2 substituents. In this case, we need to know the position relative to the primary substituent. Let's say we have phenol here. The carbon adjacent into it, we call them ortho, this position ortho. The carbon that is opposite of them, we call them para. There is only one para position. There will be 2 ortho positions. Ortho means next to, para means across. In between them, midpoint, we call them meta. There are 2 meta positions. So let's say we have nitro. If the nitro here, NO2 group, we put them here. This is going to be meta nitrophenol. Meta dash nitrophenol. The meta given dash because this is implying the position, not the name of a substituent. We're going to regard them the same way we are regarding numbers. Meta is position explaining, not name of a substituent. Meta dash nitrophenol. Usually, we're going to short them into OMP, so it's M nitrophenol. We can have pi nitrophenol, for example, but that's going to be the phenol and NO2 there. This is going to be para nitrophenol with nitro position opposite the hydroxyl. Okay, up until this, any question? No? If there is no question here, let's get back into the original one here. So let's say here we have this one here. Understand use systematic nomenclature for simple aromatic with 1 benzene ring and more substituents, 3-nitrobenzoic acid. How are we going to sketch that? As usual, we are going to read them from the back. This is initially a benzoic acid. So a benzoic acid, we have it here with COOH. This is a benzoic acid. So if we have 3-nitrobenzoic acid, we start with getting benzoic acid. This benzoic acid is going to have 1, 2, 3, 4, 5, 6. In position number 3, put a nitro. There. This is 3-nitrobenzoic acid. Now about this, 2,4,6-tribromophenol. So we're going to have a phenol. Get the numbering here, 2, 3, 4, 5, 6. 2, 4, 6, we have bromo, 3 of them. So in position 2, 4, and 6, we are going to have bromo, bromo, and bromo. Br and Br and Br. That is the way we are going to sketch a molecule if we know the names. We're going to start from the last. It's phenol. Write phenol first. 2,4,5-tribromo is the extra substituents. Number the carbon. 2, 4, 6. Put bromo into it. Bromine into it. Any questions so far? No? If there's no question here, I'm going to erase this. Okay. And I'm going to start a new recording.